So today I would like to talk about the research we have been doing in Michigan for about a decade or so, okay? And let me start with some high-level motivation or high-level goals. What we are trying to address is using connectivity and automation of road vehicles in order to improve safety, energy efficiency, and mobility. And I will talk about some of these today, maybe not all of them. In particular, I'm going to focus on adaptive cruise control quite a bit, but as Hal mentioned, I will wander into connectivity and try to emphasize the roles of connectivity in road transportation. So let me start with a little bit of a nomenclature, which I'm going to use, and it's maybe better if we kind of say it at the beginning. So this paper, I wrote it together with a couple of people from Michigan in 2020. Actually, this was published in an IAVSD journal and related to that workshop which Hal mentioned at the end. And that was a very nice place to go to in Ann Arbor in 2019 at that time. Actually, this was one of the last, in-person workshops before the pandemic started on this topic. And so what we did here is, among many things, is we categorized vehicles into different categories. Okay, so and today I'm going to use this. So I'm going to talk about human-driven vehicles, which basically we assume it's controlled by the human driver. So essentially, no automation or very, very little automation in the vehicle. And then in this case, we imagine there are no connectivity. And by connectivity, I'm going to mean vehicle to everything. So vehicle to every vehicle to infrastructure connectivity, and in these vehicles we imagine they don't have any such connectivity. We also assume there are vehicles which are connected. Okay, so they are equipped with vehicle to everything connectivity, but they're still human driven. Okay, so essentially you add a box to your car, but you still drive it. And then I will also mention automated vehicles, and when I refer to automated vehicles, I kind of talk about automation about level 2 and up. Okay, so especially today we're going to talk about ACC, and so that already level 2 is enough for many of the things I'm going to show today. But you can imagine higher levels of automation up to the level of self-driving vehicles. And then finally, there is this category which is connected and automated vehicles. So these will be vehicles which are equipped with connectivity and as automation as well. Okay, so I just wanted to kind of clarify before we get started. And really, my group is interested in a topic which is called mixed traffic. So I kind of want to define what is this. So here on the top, you can see a flow where we have a bunch of human-driven vehicles, and there is one automated vehicle who has a radar beam here and essentially running an ACC, an adaptive cruise control. Okay. Now, the kind of other end of the spectrum, and we imagine that all or many of these vehicles are connected automated vehicles, and they form a tightly controlled platoon where they are all automated, they all connected, and there is a tremendous amount of literature about this. People refer to this as cooperative adaptive cruise control. Okay, and look at that. At least if we're looking at this platoon, this is 100% automation, 100% connectivity. And the research we are doing is somewhere in the middle. So we have, some automated vehicles and some human-driven vehicles. And in this case, I'm showing scenarios where the automated penetration is relatively low. It's essentially only one vehicle out of these is connected automated. In the meantime, as I go from top to bottom, the connectivity penetration increases. Okay, so we can have more and more vehicles which are human-driven, but they are connected. And this is what I'm going to focus today, and in particular, how to go from this adaptive cruise control to connected cruise control, and how what kind of benefits we can get out of it. So, okay, wait. Hopefully this works. Right. Yeah, so here are a couple of publications on this topic. They are all available on my website. And I'm also very happy to share with you if you have any particular interest at the end. So just wanted to highlight that they are all there. But let me start with some very simple things. So, at the University of Michigan, we are very close to Detroit and the auto industry. So we do a lot of vehicle dynamics and control. Okay, and these are kind of some basic knowledge which we also tell to the students. So I want to kind of review it so we are on the same wavelengths. Okay, so this is a very prototypical model of longitudinal vehicle dynamics. And what you can see here is that we represent the position of the vehicle and the velocity or speed of the vehicle along the road. But there are additional effects which can influence us. In particular, we have gravity. We also have rolling resistance. We also have air resistance. And this last term here, which I'm going to highlight, if my mouse works. Yep. So this one is related to the torque, which we are putting on the wheel. Okay. And I immediately put something here. So there are two important quantities I'm highlighting here. So first of all, we can't put as large wheel torque as we want. Okay, there is some kind of saturation function related to that. And on the right, I'm showing this saturation function. Essentially, what it results in that we can't output in terms of desired acceleration as large as we want. Okay, so we will be limited between, let's say, somewhere maybe -8 to +3 meters per second square in case of a vehicle. As a matter of fact, it's a little more complicated, as this other figure shows here, that the power limit of the vehicle also matters. Okay, so how many horsepower you have, that is going to influence in particular the high velocity regions. And these are very general, so it actually applies for vehicles of pretty much any powertrain, because it simply says that you can't have infinite torque and you can't have infinite power. There is another important quantity here which I would like to highlight. And this is the fact that we can't even immediately launch these torques on the wheels. We have some delay in the system, and this powertrain or brake delay can be quite significant even in automated vehicles. So what I'm going to do today is that I'm going to simplify this model and essentially omit these first terms here, assuming that some lower level controller can take care of it, and then focus on this simplified model, but it's basically a second order integrator with a time delay. And it's a very simple model, but it still allows us to design controllers for the vehicle. Okay, so of course, this is a lonely vehicle on a lonely road. We're more interested in what happens when the vehicle has to respond to other vehicles ahead. So when we talk about adaptive cruise control, then at least have to have two vehicles. Okay, so this automated vehicle is the one which I'm trying to control, and there is a human-driven vehicle which I'm sensing via a radar in this case. So you can also use cameras or LiDAR or whatever sensors you have, but you have to have a line of sight to be able to see this vehicle. And again, this is the simplified model. I changed the first equation. Rather than using the position of the vehicle, now I'm using the distance, because that's kind of part of the goal this vehicle wants to achieve. It wants to keep a distance from the other vehicle. Okay? And if you look at, actually now there are standards about what is required for ACC. So there is typically a desired behavior which is saying that the vehicle should have a set speed. Okay, so we shouldn't go faster than that. And also, if the distance gets kind of smaller, so traffic is getting denser when this distance gets smaller, then we try to keep a constant time headway here. So this kappa gradient of this range policy, or some people call it the optimal velocity function, is actually going to be equal to 1 over kappa. So the time headway is 1 over kappa, and kappa is the gradient. Okay, and this is one of the important parameters. If you buy an ACC vehicle, then actually often have these adjustments. You have like 1 bar, 2 bar, 3 bar, 4 bar. 1 bar actually corresponds to a really high kappa, which means a very short time headway, and 4 bar typically is more relaxed. So essentially that means that you have a smaller kappa and a larger time headway. Okay, so this is pretty much baked in into every vehicle on the road which is ACC. And then for low speed, you typically want to stop, right? So you have to shift this a little bit, so you stop in a reasonable stopping distance. Okay? So arguably the simplest algorithm to be able to maintain it consists of two terms. The first term is directly trying to adjust the velocity to this range policy. Okay, so that's kind of maintain the distance with respect to the velocity, or the velocity with respect to the distance. Okay, so this is going to be the control input which we put out there. And the second term is simply trying to match the speed to the vehicle ahead. Okay, and this kind of controller shows up a lot in the literature and also shows up in the traffic flow theory literature, but they often refer to this as the optimal velocity model rather than a controller. Okay, but now if I put this into this equation, essentially I'm going to get some car flowing dynamics with some time delay. Okay, now in order to analyze this system and design, right, we typically want to make sure that the system has an equilibrium. Okay, this means that the velocities are the same, and actually the distance is given by this range policy. So this works out pretty nicely. But we're also interested in how the response of the blue vehicle is going to be for the motion of the red vehicle. Okay, and for that we typically use a transfer function. So we linearize around this equilibrium and look at the perturbations around the equilibrium in the speed of the red vehicle and the speed of the blue vehicle. And this transfer function is what we use in order to evaluate the dynamic behavior of the system. Okay, so I would like to spend a couple of slides on looking at it, just to kind of build up the tools which we typically use to design ACC, and then I'm going to show you how it actually works in practice. Okay, so there are two kind of stabilities which we are very much interested in when we design an ACC. So one is we refer as planned stability. And honestly, there are different ways to call it, but this is just the standard notion of stability of dynamic systems that everyone refers to. If the system is stable, okay, then when the driver ahead is running with a constant speed, we shall be able to approach this speed and going to follow it eventually with the right distance and the same velocity. And then if the system happened to be planned unstable, okay, then this would not happen, and you can see immediately this would be a very detrimental behavior. Essentially, a planned unstable vehicle will very likely hit the one ahead. Okay, so if you are in the industry, you definitely want to make sure that your system is planned stable, because otherwise it would be not safe. So the way we evaluate it for our transfer function, then we look at the denominator of the transfer function. We refer it as the characteristic equation, and then we calculate the characteristic roots. However, if you have time delay in the system, which I'm showing here in this e to the s tau term, then actually it turns out you have infinitely many characteristic roots. So this is one of the property of time delay systems, and we really have to take care of all of them and keep them on the left-hand side in order to make sure that the system is stable. Okay, so the task is a little bit harder than for ordinary differential equations when the spectrum is just a finite number of eigenvalues. Still, we can actually ensure it and draw these things which we refer as the stability chart. Okay, so in this particular case, I'm plotting the stability chart for a particular value of the delay and actually a particular value of the time Hadway kappa, which I didn't know here, but it's also 0.61/second. And I'm plotting this chart on the plane of the control gains, because these parameters are the ones which eventually we can design and when we implement the controller on the vehicle, so we can actually tune these and we can choose one nice combination which has to be, of course, in this planned stable area. Okay, now there is if you look at the eigenvalues, then indeed, as I mentioned, inside this domain, all the eigenvalues or characteristic roots are on the left-hand side. If you are outside of area, then you have some characteristic roots which are responsible for this instability. Okay? Now, there is another notion of stability which we also very much interested in. In the control literature, people call it an input-output stability. A more specific version of it we refer as string stability. Okay, and the string stability comes from the fact that after all, there could be many vehicles after each other and they make a string. Okay, but I'm going to explain it just in terms of two vehicles using the velocity. Okay? Basically, the idea is that if our leader is going to do some kind of velocity fluctuations around the steady state, then our follower automated vehicle is supposed to actually decay them and make these amplitudes smaller than the leading vehicle. Okay? If the system is string unstable, well, it's probably not a big issue in terms of safety if these oscillations are not really large enough. But it can be detrimental in terms of the traffic flow, because if all vehicles are doing this, then their motion is going to be leading to eventually congestion. Okay, and there are a few new papers on the market which saying that essentially many of the ACCs which are sold today are string unstable, and the reason for that is because the companies may not be interested in that much in the overall traffic behavior, but they're more interested in the passenger comfort, so they tune these controllers in order to achieve that. Okay. Again, there is a nice condition which allows us to evaluate string stability, and we are going to use again the transfer function between the two vehicles. And if the transfer function is smaller than 1, then actually for all frequencies, then we refer the system to be string stable, at least in the linear level, and in particular you have to specify what norm you're using and so on. Okay, I'm not going to get into these details, but the nice thing about this condition is that it's computable, and again we can actually turn it into a stability chart. So what I did here, I zoomed into the previous stability chart. That's why everything is light gray, so this is all plane stable, and then I drew this diagram here, okay, which is the string stable area. Okay, and an important thing again is that if you didn't have delay in the system, then this entire big upper part here would be string stable, but because of the delay, actually we're going to have a much smaller domain. Okay, now if you are in this domain, in this string stable domain, then your transfer function is always smaller than 1 for all frequencies. If you are outside of the domain, then actually the transfer function is going to be larger than 1 for some frequency domains. It doesn't necessarily larger than 1 for all frequencies, but some frequencies. And these are the frequencies your vehicle is going to be sensitive to. So if you get excitations from the leader in these frequencies, then essentially you will have this issue of string instability. Okay? And a very important thing happens here is as you increase the delay, there will be a critical time delay, and below the delay, basically there will be no string stable area. Okay, so and interestingly, this is nothing else but half of your time headway. This can be shown analytically, and so what it means is that if you try to travel with a 1 second time headway, you cannot have larger than half a second delay in your system. Okay, or vice versa, if you have a delay given, for example in this case 0.6, your time headway has to be at least 1.2 seconds in order to have the possibility to have some string stability. Okay, and it's a very strong condition on the system, and I will show you that actually this is true in experiments as well. Okay, so these are the experiments which we were running in the last couple of years. So what you see here on the left is a test track of the University of Michigan, which is called M-City, after the M, which you can also see painted here. It's currently led by Professor Henry Liu, and it's a fantastic test track in the sense that it's, apart from it have a lot of functionalities, it's very close to us, and we have access to this, so we can actually play with vehicles in a way we were not able to do it before. So the test we were running here is relatively simple. We were basically following the other vehicles. So now you see basically the camera from the leading vehicle looking back to the automated vehicle. So the automated vehicle is following us. And then the test we were running consisting of acceleration, braking, and also some constant speed sections. So this is one of the constant speed sections. You will see this is where we start to accelerate. And then actually the other vehicle is going to lag behind a little bit, right? And then eventually catches up with us. Again, we run a constant speed section, and there will be a relatively harsh braking at the end of this part of the section. We are taking the curve, so we are somewhere up here on the northern part of the test track, and soon you can see that it worked really nicely. The vehicle actually behind us stopped. The driver was, well, he was just there for safety, but he was so relaxed that he even put out his hand on the vehicle. Okay, so let me show the data we collected through this because it's very interesting. So this is essentially one of the good tests. So I'm showing the velocity of the leader and the velocity of the follower on the top. Okay, I'm showing their acceleration at the bottom, and I'm also showing the corresponding headway. And so an interesting thing is, so red is the leading vehicle, okay, and blue is what we measured from the vehicle, and this black line, it actually corresponds to what the model would have done. So if you run a simulation with that simple model I showed you, that would be the black dashed one, and you can see there are some differences. For example, here the real headway was a little larger, so we lagged behind a little bit, and it's exactly related to the fact that this vehicle had some power limits, and as the speed got higher, it had difficulty to catch up. Okay. Now, if you look at, in particular, the acceleration, you can see that there are some small vibrations, but it generally does well. Okay. And if you ride this vehicle, it would feel quite comfortable, as a matter of fact. Now, if you change the parameters for this alpha and beta, in particular here in the acceleration, you can see that the vehicle gets a little more nervous, and there's a lot of these high frequency vibrations, which exactly comes from the fact that we have a time delay in the system. And if you ride this vehicle, you would get motion sickness very easily, because this is not very well tolerated by the human body. Okay, so apart from leading to string instability. However, these signals are very different from those nice periodic signals which we use to evaluate string stability. Okay, so in order to kind of use this data, we had to do some Fourier analysis, and what you can see on the top is actually this nice run, which was the first run. Okay, and I'm showing the FFT of the speed, and on the right I actually show the ratio between the two. Okay, and you can see that, well, the theoretical one would be always below 0, but the practical one is kind of hovering around 0. This is on a scale, a log scale, so that's why this 0 is actually corresponds to the transfer function magnitude being equal to 1. Okay, but now you can see in case of the bad run, things get much worse. As a matter of fact, in this case, both the theoretical and the experimental data shows a pretty large peak here. So it actually shows that we have a string instability in the system. And to quantify it, what we basically do, we integrate these red parts, okay, and if this index, which we call the string instability index, this is very useful to evaluate the experimental data, is larger than 1, then basically it counts for this larger than 1 area. So if this is large, that means the system is quite string unstable. So you don't want to choose the particular parameters for your ACC system. Okay. So here is how it looks, and now I'm put these string instability indices on the top of the string stability chart. Now the string stability chart is drawn for 3 different delay values, just to kind of see how robust we are to that. And again, the size of the points are related to how string unstable you are. So what it shows is that this middle area here is actually doing pretty well, and that's exactly where we have string stability according to theoretical calculation. But if you are outside, and this Z was actually the bad data which I showed you, then you can have much worse behavior. Okay, so this allows us to, number one, justify the theoretical calculations, and number two is really choose and fine-tune these parameters in order to have a nice ride. Okay, so that's kind of the typical way someone can design a string stable ACC controller. Okay. Now let me show you a little bit more on this. So, in the traffic flow community, there is a big question. Okay, so how does these ACC controllers are going to influence when we mix the traffic, when we mix them into the flow? Okay, and what I'm showing here are actually 4 different simulations for 4 different penetration levels of automated vehicles. Okay, and I'm actually using exactly that nice design which I showed. And the human drivers are actually described by the optimal velocity model in this case, but you could use the IDM, the intelligent driver model, if you want. That wouldn't change too much. And what happens is that if we only have human drivers, then indeed the system is string unstable. So an initial braking from the black vehicle at the front actually going to propagate and keep increasing. Okay. If you mix AVs to the system, you can see it starts to get much better. For example, down here, I think it's like maybe 15% penetration of AVs. It's about 33% and 50%. And indeed, as the AV penetration gets better, because these vehicles are designed to be string stable, then we start to have better behavior. And maybe around 50%, actually, you reach string stability. So that's a pretty high penetration of AVs required to actually stabilize the flow. And just to mention here, the human parameters were also obtained from real data, so they are not just made up. So these human drivers are really drive according to this way. So these are realistic parameters. Okay, so it says that if we have AVs and they drive nicely, and the second condition is very important, then actually we can improve the traffic flow significantly. But it also says that we need a large penetration of these vehicles in order to make sure that the traffic is actually string stable. Okay? So now I would like to switch gears and talk a little bit about connectivity. So far I haven't really mentioned any of these. These vehicles could achieve this motion just by optical sensors, so radar, lidars, and cameras, and that's how the current AV industry is rolling these days. Okay? So let me show you what happens if we add connectivity to the system. Now, in order to explain the concept, I'm going to look at probably the simplest possible scenario. Okay, so I'm only focused on these 3 vehicles. The first 2 vehicles are human-driven vehicles. Okay, they are not automated by any means, but the first vehicle here is actually have connectivity. So what it means is that this connected automated vehicle is able to sense the vehicle ahead by the range sensors and able to get motion information from beyond the line of sight using connectivity. Okay, and when I turn it into the idea, the way of how to do the control design, then this first part of the controller is exactly what we had before. Okay, and the second part is actually coming from this connectivity, and as you can see, it's very simple. It's just a velocity difference. So this CAV is trying to match its velocity not just to the vehicle ahead, but also to the vehicle which is 2 vehicles ahead. Okay, this is that simple. At the same time, I'm using the same range policy of following. I didn't change anything on that. Okay, now the system becomes a little bit more complicated, right? Because we have to kind of count for more vehicles and think about string stability a little bit more carefully. Okay, now if you look at what we did is we basically again go to the level of transfer functions and we figure out how the HV responds to the CHV and also how the CAV responds to the HV and to the CHV, and these are represented by these transfer functions, and we call them link transfer functions after you linearize your equation of motion, that of course includes modeling, in this case the human-driven vehicle with some crowd following model. Then you can actually establish these transfer functions. Okay. However, if you just have these, they are not enough to evaluate string stability. But we came up with this idea called head-to-tail transfer function. Okay. What the head-to-tail transfer function does it basically accounts for all ways of how the information can reach the CAV. In this particular very, very simple scenario, there are two ways, right? You either go along the chain from the black to the red to the blue, or because of the connectivity, you can go from black to blue immediately. Okay, so the controller can actually use this information, and we have to count it into the controller when we do this, and this is how we calculate this head-to-tail transfer function. We actually have a general formula for arbitrarily large connected vehicle networks. Okay, so if you give me n vehicles with an n by n connectivity matrix, this can be calculated. Okay, it's a very powerful thing, and let me show you why. So first of all, if now we want to talk about head-to-tail string stability, this is a very good tool to use. Okay, and we can start to do what we call head-to-tail string stability charts. In this particular case, I'm using these beta 1 and beta 2. There's some extra zeros here, but they mean the same, okay? So these two different control gains in order to figure out that what betas I can choose to make this system head-to-tail string stable, okay? So let me show you first what happens if we do not have connectivity, okay? So I'm setting the beta 2 0, this second term which I just had added, to be 0, okay? If that happens, then basically here are the corresponding frequency plots, okay? So the human is represented by this T12, okay? That is very string unstable, okay? There is a very large domain of frequencies, but it goes above 1 quite significantly, okay? Now in the meantime, this black is actually represents this T10, so how the blue vehicle responds to the red vehicle in this case. And you can see that that's indeed string stable. So if I only had the red vehicle in front of me, then this blue vehicle would be able to decay the corresponding perturbations. Okay. However, what we are interested in is this blue head to tail, which is basically checking out what is the perturbation going from the black to the blue, and that is still about 1. Okay. If you add the connectivity, you can actually push it below 1, okay? And in this case, this becomes a really nice and string stable system, okay? And it's quite a dramatic improvement. And the only thing we did, we added connectivity between the lead vehicle and this last vehicle, okay? Of course, we want to make sure that this is scalable for larger systems, okay? And we have the right amount of modularity, I believe, because we are not requiring these guys to cooperate in this case. We can't, right? The human here is just human. We simply use extra information at the CAV. Okay? So now if I show you some experimental results. So the simplest scenario, actually, I shouldn't have put this radar beam here, right? Because this is a human-driven vehicle. So we ran it with all humans, and again, we went back to M-City. We accelerated, we drove some constant speed, and eventually what you see here is the braking event. Hopefully the video is visible. And what happens is that there is a sequence of brakings, and eventually the last vehicle, it has to stop. Okay, unfortunately the video doesn't work very well, but let me show you the data, maybe that shows something. So the first vehicle did like about a half a G braking here, okay? And the second one, it was also human. It actually did more. And finally, the last human did about, this is an emergency braking. This is 1G, pretty much what the vehicle can do. Okay? And with that, it could stop safely, but it was a very, very uncomfortable ride. And my students always complained at the end of the test because, you know, if you have 1G acceleration, essentially your entire weight is on the safety path, right? So that means that it hurts by the end of the day, of course, but we need that for safety. Now, if I change it to an automated vehicle, which is basically saying we're running ACC, right? So now the figure is correct here, and this is an automated vehicle. Let me not show the video because for some reason it's not playing very well, okay? But I show you the data. So the data shows that, as I mentioned, this is kind of this marginal string stability, right? That was exactly the case when we had like 50% penetration of AVs. we were getting to this marginal string stability. So what it means is that it's doing much better than the vehicle in front of it, but in terms of head to tail, it's still doing roughly as bad or as good as the front vehicle. Okay, so that and this is still a harsh braking. You would really know if someone does a braking like this. However, if you add the connectivity, you can see you get into this green zone here. So your acceleration actually go around minus 2.5 meter per second. That means if you have a cup of coffee in your hand, not a droplet would spill out. Okay, this is a very nice and very smooth ride. And the only thing we did when we counted in this additional effect of connectivity. Okay, so obviously this has severe safety implications, right? Because especially now in Michigan, you know, it's very slippery out there. You would not actually be able to do these very harsh accelerations, okay? Because your vehicle would slip. But also there is a high level of comfort, which is helping us here, okay? And the original motivation of us was also making sure that this is helping the flow of the vehicle, traffic flow of the vehicles. And I will show you that actually it is the case. This is indeed scalable for a larger number of vehicles. Okay. So let me show you here a simulation. So the top shows the scenario for mixed traffic system where we don't have connectivity. Okay. We only have AVs, and as you can see for this particular motion, if every second vehicle is an AV, then we indeed achieving this mild string stability. If every third vehicle is an AV, right, so 33% penetration, then we kind of at the limit, okay? So for this particular signal, it kind of shows that it levels out. If you do a slightly different signal, you may get a little increase, okay? The same thing is shown with connectivity at the bottom, okay? Where you can see how dramatically it improves the behavior, right? So in this case, it decays much, much faster, the waves, okay, with the same penetration as we had AVs above. And if we have even lower penetrations, we can get very nice behavior, okay? So for low penetrations, the AV was doing some marginal case. When we do CAVs, we still have a very nice and beautiful behavior, okay, almost matching the higher penetration. So this tells us that if we have connectivity in the system, then much lower levels of automation can actually give us nice traffic flow, okay? It does require, of course, that these vehicles are designed properly, and if you do so, then you can actually achieve this behavior, okay? Now we wanted to put it to the ultimate test, and so we went out to a stretch of a road. So this is an 8.6 mile long stretch of road with basically no intersection. So this, all the other vehicles who try to come here has to stop. Okay, so it's the American dream. And then you can also see that there were a bunch of vehicles. I mean, these are just normal rental cars. But the big question was always who drives the Dodge Challenger. And I think this day, the guy who's standing there, he was the happy driver. Okay, so what we did was we put a chain of human-driven vehicles along this stretch of a road, and then we asked the first driver to drive and basically make some breaks along the way. And these brakings are kind of trying to mimic what happens in traffic. You know, people often have these change of speed, and we wanted to see how does it propagate along the chain of the vehicles. And what I'm showing here is when we ran an ACC, okay, this was a nicely designed and tuned ACC, and what you see is that while the humans are actually increasing the corresponding perturbations as they propagate along the chain, while the AV cuts back a little. So if you compare the blue one and the red one, right, the blue is doing a little better than the red one. So experimentally, we were able to show that indeed the AV has a positive effect, okay? However, once you start to add connectivity, and this is the scenario I showed you before, okay, things starts to improve. So already here we can see improvement. And it turns out it doesn't necessarily matter whether you talk to the vehicle, which is 2 vehicles ahead or 3 vehicles ahead, you know, the same level of connectivity penetration, you start to get benefits, okay? And of course, you can keep increasing the level of penetration and you can get better and better behavior. Indeed, at some point you will saturate, but you will see here in this particular experiment, the blue vehicle is doing pretty much as good or even better than the brown vehicle at the front. So this, for this zoom here, this was very nice, okay? And it has a very profound effect on the flow. Now, of course, you may say, well, wait a minute, you picked the nicest plots and you're showing it to us, okay? You're hiding something. Well, that's true. I did pick the nicest plots, but let me show you that I'm not hiding nothing. In particular, one interesting thing was when we had these different runs, we evaluated the energy efficiency, okay? And for this, we did a lot of evaluation, not just for a single braking and so on. And let me try to show you what happens here. So this W is the measure of energy consumption of each vehicle. Okay, so it's basically velocity times acceleration, but we only take into account the accelerating part and not the braking part, because I'm imagining that that time we are not burning fuel. This is probably more true for new vehicles than the old ones, but that's a simple measure of energy efficiency. Okay, and you can see, and it's normed by the vehicle mass to kind of be able to compare them. So as we go along this chain from the right to the left, which is basically from brown to purple, these numbers increase. Okay, humans are string unstable, they keep increasing the energy consumption. Okay, but interestingly, when you reach the AV, okay, it cuts back all the time. So the first experiment was done just ACC. It cuts back 7% fuel consumption on average. And if you run the high connectivity, that was the last experiment, okay, then you actually cut back 24%. But one interesting thing to look at the two compared to each other, okay? So what it tells us is just by adding connectivity, which is a very cheap technology compared to automation, actually we can have about 20% energy savings just by the connectivity, okay? Interestingly, even the guy behind us saved 7%. Okay, so now looking at this time of century where we really want to focus on saving energy, this is a very, very effective way of doing that. And again, not just the connected automated vehicle, but vehicles behind, i.e., kind of the overall traffic flow, can benefit from this. Okay, so it's a very efficient and effective way of increase the efficiency. Okay, now let me tell you maybe one last thing about what we are doing now. Indeed, there is an issue here, which is, well, how long it's going to take to get these vehicles connected. Okay, well, at this point the connectivity level is very low, and do we expect it to increase in the next decade or so? It's going to take a while until it picks it up. Probably going to be faster than automation, but it's still going to take time. Okay, so we really have a connectivity gap here. In a realistic situation, it might be that there is a vehicle in front of you which is maybe 100 vehicles ahead or 50 vehicles ahead. That means that you can't really communicate it directly. But we can actually use infrastructure to support it, right? So the connected vehicles can actually talk to these roadside units, okay? And the information can be, through the internet, put to other RSUs where actually can be sent. In this case, we are using a truck, so that's why I call it a connected automated truck or CAT. And this vehicle actually can still benefit from the information which is coming maybe a mile ahead, okay, or maybe 2 miles ahead. So that's a big improvement, and we certainly believe that automation and connectivity should come in hand. It kind of reminds me a little bit that now we ask these AVs often to run our 20th century infrastructure, right? So basically we say, go there in the wild and just make sure you can drive there without any infrastructure support. It would be equivalent if 100 years ago, they start to make the 4T model and say, we want this vehicle to drive anywhere, any country road, on the field, and so on. Actually, there were people who were saying that. There was a big promotion and asking Ford to make vehicles which are doing that. But which was a very different route if you see the last century. we built the right infrastructure for those vehicles, okay? And eventually they can go in the mud, but they go very, very slow. But now we have the road network, we have the physical infrastructure to support it, okay? We firmly believe, and this is a project supported by the Center of Connected and Automated Transportation at the University of Michigan. So they also believe in it, that this connectivity is going to be crucial to build up the cyber infrastructure of the future automation, okay? And this is going to have a large effect on that. So this project is still going. So currently, let me skip this part. We are installing RSUs, so roadside units, along this highway I-275, okay? So you can see it's a relatively low-cost installation. So this is an existing MDOT pole, okay? And this is the device which we installed here, okay? And basically the only thing we need is power, which we are getting from this MDOT cabinet. So they are very nice and provide support for us for the installation. And it's a really great partnership between the University of Michigan and the Michigan DOT. And you can see some of the experiments which we already ran. I mean, this is just a sketch, but there was real data flowing here, which is one way is basically that the green vehicle is talking to the RSU, and the blue vehicle who cannot have direct access to the green vehicle, which is too far, they actually can talk to the RSU and receive those information. Okay, so we have some experimental data which is already flowing. Okay, so let me conclude. My time is getting close to an end, and so let me start with that. That we really want to focus on these high-level societal goals, and then as engineers, we need to turn it into some control objectives. In this case, control objectives of these connected and automated vehicles. And as I hope to demonstrate today, that connectivity together with automation, it may help achieve a better performance and efficiency, both at the vehicle level, okay, so that helps the customer who is buying that vehicle, which is very important, as well as the system level, i.e. we have those, trying to achieve those high-level societal goals, and we are getting there, okay? So as my last slide, I would like to mention, of course, I don't do this research on my own. You can see many faces here, and also many companies and associations. Again, Ford, Toyota, and Navistar, they collaborate with us. Consignia is a communication company who's providing us with these devices. I already mentioned MDOT and CCAT, and then you have seen a lot of videos which we shot at M-City. But we also have collaborations across the nation and across the globe. There are a couple of professors at Caltech and also at Budapest we are working it. And in the US, Clemson, UCSD, and Delaware, where most of the collaboration happens. And of course, these professors at the bottom, they are all at the University of Michigan. And I have to mention that, we have fantastic collaborations here, which helps us to achieve these goals. So I guess with that, thank you very much for your attention. And if you have any questions, I'm very happy to answer.
Okay, thank you. Thank you, Dr. Gabor. That's very excellent presentation. The audience, I think now if you have questions, please feel free to unmute yourselves, or you can also type a question in the chat box. Dr. Lava, please.
Yes, thank you. Great presentation, Gabor. Thank you for being here. Really enjoyed your talk. The second case that you mentioned didn't include delay, right, for that second part?
Can you please repeat? You were breaking up, at least on my side. I don't know whether other people heard.
Yeah, Dr. Lava, we
clearly
can repeat. Yeah.
Yeah. So the second part with the connectivity.
Yes.
My question is, if you could include a delay there, would you obtain the same insight as in the first part of the talk?
We did include the delay. So all of these results we got analytically, they include the delay.
Right, but hold on. I think I mean a delay due to connectivity, because the delay you included was related to the torque, I think you mentioned.
Yes, yes.
Also,
So
if you
that
could
would be,
clarify the nature of the delay. Yeah.
yeah, I agree. So yeah, that's a very good question. Indeed, this delay is really coming from two parts. So that torque delay is always there, right? That the vehicle delay, because that's how the vehicle operates.
Yeah.
But as you mentioned, there can be delays coming from the connectivity. So the current technology we're using is sending messages in every zero point 0.1 second. So that means that if all the messages delivered, then our delay becomes between like 0.1 and 0.2 seconds roughly, coming from the connectivity, and we have to add it on the top of the vehicle delay. Now, if we start to lose packets, then things starts to get tricky because the delay can go up. And indeed, there is a level where the connectivity is broken up so much that the delay is too large, and indeed the controllers can lose their performance. The way we investigated it is that we modeled the packet deliveries using stochastic processes, and because they are following, some kind of Bernoulli process, and then basically we were able to ensure string stability on the mean and on the second moment level. So that the math gets more challenging and more important, but you can still find parameter regimes where you can ensure the head-to-tail string stability.
So roughly the same conclusions remain valid?
The same conclusion is valid, but of course the performance will degrade, right? So so there will be a performance degradation as the communication gets worse and worse. So there is the performance is inversely proportional to the quality of the communication.
Okay, great. I think Danja has a question.
Oh, yes. Hello, Gabor. Thank you very much for being here. I really enjoy your presentation. Very interesting. I have a quick question. You mentioned that the truck case, it can benefit even the information is available like 1 mile downstream. So I'm wondering how the improvement happened.
Yeah, so that's something we are currently working on. So there are two issues. So one of them is that somehow we need to get that information to the truck. So that was the technology I mentioned. The second thing, I need to kind of let the truck know is like, okay, so how can you use this information? At this point, what we are using flow models to basically propagate these perturbations from the vehicle which sends the information to the truck, okay? So essentially this allows the truck to have a potential profile ahead of it, which is expected to run, right? So if the previous vehicle went through a congestion, then it already has it in history, and then the truck knows that, oh, that's gonna be my future, right? So this is, we're using at this point, simple LWR, New World type of models to do these things, because we need to focus on devices. And so then it can plan, right? So those controllers are going to be different. They are not these very simple reactive controllers only, which I was showing, but it actually uses that velocity. So typically it does some optimization based on the available profile. And that's how it tries to save the energy.
Oh, I see. Yeah, that makes sense. Another question I have is that you show the very elegant results when you have in the 3-vehicle case, then you have the head to tail. So I'm curious if the vehicles have different controllers, do you still have this very elegant way to put them together, or it can become more complicated?
So I think the method still works. So this head to tail actually stability can be computed. As a matter of fact, for the human driver, we used a slightly different model in this case because we were modeling that differently than the machine. So it does work, but of course, you might have a lot of parameters to play with, and then it may be harder to kind of get the results nice and crisp if you have larger systems. But the methodology it does work actually. So head to tail transfer function can always be calculated the same way from the link transfer function.
I see. Very good. Thank you. I think we
welcome.
have some other questions in the audience.
Yes, we have two questions in the chat box. Before that, maybe I can have a follow-up question on the delay. I'm interested in, because you have shown some experiments in M-City.
Yep.
I'm curious, are you able to measure some empirical delay, especially those torque delays from the experiment vehicles?
Yes, so we did measure that. It's both from these vehicles, and also we did some measurements with trucks. The conclusion was that these delays in the vehicles which we were using, the powertrain delays, were on the range of maybe 0.5 to 0.6 seconds. So we did it basically just directly looking at what command we gave and what the vehicle was doing. So there was a direct checking, but we also did some Bayesian identification. So we basically loaded the Bayesian estimators, and the estimators told us this was your delay. And then of course in that case we got a distribution which was centered around 0.5, 0.6 seconds. For the trucks, this could go up to something like 0.7, 0.8. And the reason for that is because they're using, in particular in the brake system, they're using pneumatic brakes, so air brakes, right, rather than hydraulic brakes, which normal vehicles are using. That's one of the reasons. The other reason is that their engines, which of course may eventually get to electric motors, their engines are more sluggish, right? So that makes them larger delays. And so that was what we observed, this, the normal vehicles 0.5, 0.6, and trucks about 0.7, 0.8. But of course, it's a limited set of experiments, but through the vehicles we were playing with, this was quite consistent.
Nice, thank you. We did similar experiments and the result is quite close. We also observed around 0.7 or even 0.8 delays from some like commercial ACC products or the daily car models we used. Yeah, but I'm afraid those experiments cars you used there should be different from maybe those daily car models we find here.
So I think the difference is that we built our own ACC, right? So that was, which is good and bad. It's like, meaning it wasn't a commercial ACC on one hand. On the other hand, we know what was going into it, right? Because in a commercial ACC, you kind of have to backward engineer what they really put into the system.
Yeah.
In this case, we had direct access.
Yeah, I'm also curious, what is the general low-level control system you used on the experimental car? Because this is not captured or modeled in the whole system. Looks like the transfer function is only from the planner or the controller you mentioned here. So do you see any potential impact of some good performance or lower performance, low level, that could affect the results here?
Yes, that gets important. So what happened is that in case of the personal vehicle, well, we did a lot of lower level control, but basically what I can say that if we didn't have significant elevations, then we didn't have that much difference from this simple model. Okay, so what it means is the vehicle roughly behaved as like those controller wanted it. In case of trucks, this is not true at all. So in case of trucks, we played a lot with the lower level control, and basically we had to build in compensations for the grade and rolling resistance and air drag, because it was too large. So if we didn't do it, then the vehicle wouldn't perform at all like what we wanted in the higher level. So in some sense, my feel about it is that the bigger the vehicle is, the harder this problem gets, because the power to weight ratio changes quite a bit, right? So if you have a personal vehicle with 100 horsepower, that's 2 tons, but this trucks which we had actually was only maybe 400 horsepower, and it was 30 tons. So yeah. It's a much different ratio.
Yeah, we share the same concerns here. It looks like the great impact on the low level and on the overall screen stability needs more investigations. Thank you for your answer. Yeah, then I will read the two
I'm also
questions.
happy to share the results, but if you have something which you guys already published on it, I would very happy to read it. So if you could share it with me,
Sure.
that would be fantastic.
Thank you. We can talk later about that. Yeah.
Sure.
We also have two questions from the chat box. I will read them out. The first question is from Mohammed. And thank you for the wonderful presentation. I had a question about the connectivity. Was it using CV2X or DSRC technology?
Oh, that's a good question. And the answer is both. So actually we did a technological change during the last 5-ish years since we have been running these experiments. So in that, Comsignia was a very nice partner because the transition from DSRC to CV2X for us was quite seamless. Essentially, the higher level APIs we were running were the same. So this helped a lot for us to do the transformation. We did some comparative measurements between DSRC vs CV2X. In these experiments which I showed you, you wouldn't really see too much difference because for the distances of these car followings, that they are both very reliable. CV2X, we found a little larger range of communication, which is useful for us in the infrastructure project because we still only can put on a finite number of roadside units, and we have to kind of optimize where we put them, etc. So it was a little larger, and that's beneficial, but we don't quite know why, right? So did they just crank up the transmission power in the chips? We don't know. So both work. So, and I think I'm kind of saying is that it's important as well that we don't kind of get hooked on a certain technology and only that can work. What we find is that there is an evolution, and then we kind of went with that flow, and the ride was relatively smooth due to the support of the companies.
Okay. Another question from Nicholas. Have you investigated the usage of gain scheduling for those alpha and beta values to achieve the same level of fuel saving results for different headways and time delays?
The short answer is no, we didn't do that. But it's a very interesting kind of concept, so maybe we should look into that. Rather than doing gain scheduling, we did some different control design. So this is a collaboration with the group of Professor Ardal and Vahidi from Clemson University. And then we basically, rather than using these simple alpha beta controllers, we started to use model predictive control. And it turns out that it can actually have, so better fuel economy or energy efficiency if we design the MPC well, right? So it by no means these simple controllers which I showed today are the best. They may be the simplest, and it was relatively easy to implement them. But yeah, there are gain scheduling, or in our case, MPC is something which can potentially improve the energy efficiency.
Okay, thank you. Looks like we have no more new questions. All right, I think that will be all for the presentation. Thank you, Dr. Gabor. Thanks for the nice presentation, and thank you for all the audience coming here. And yes. In the last, I would like to share a little bit of administrative announcement here. So the plans for the February and the March, we will be closing the series of ACC webinars, but we still have 4 from Dr. Alariza, Raphael, David Kane, and Dr. John Ray. And after the ACC webinars, we will move on and shift to some CAV studies, which will be starting by Dr. Jatima from UCLA to share his recent works. So thank you for all of you. Thank you for your attention here, and would like to having you in the future ACC webinars. Thank you. You'll have a nice weekend. Bye-bye.
Thank you very much, and I was glad to be here, and thanks for the nice arrangement for it, and looking forward for the future seminars.
Sure. Thank you.
Thank you, Gabor.
Bye-bye.
Thank you,
Bye-bye.
Gabor. Have a great weekend.
Thank you. You too, guys. Take care. Bye-bye.
Bye.
Bye.